Scoop! Scoop! Scoop!
Our robot is climbing up either this ramp or the pipe ramp and placing a ball on the tic-tac-toe board. We have to fit inside a 12 by 12 by 12 box and use limited materials.
So the original idea was to have an ice cream scoop design, a curved surface that would come over the ball with Velcro inside so it would stick to it, and we'd have a poker on the middle without Velcro to push the ball out. We decided that was too risky though, because with Velcro on the board, that would get a little bit difficult, so we decided against it.
So we used pulleys so we could take turning and have four-wheel drive to make it up the pipe ramp. We also calculated our gear ratio. So we used a factor of safety of 3 and estimated that our robot would be around 2 kilograms, and that gave us a gear ratio of 3. But just to be safe, we did the maximum that we could get with the gears that we had. So we did a gear ratio of 4. We also wanted to elevate the chassis so we could make it up the pipe ramp. So we made sure to have our motors on top of the chassis and the axles of the wheels below the chassis. But that also meant that we had to find a way to get the gears to go through the chassis.
So the size of our wheels is 4.25 inches in outer diameter. We included small bumps and treads that run along the outer rim of the wheels to increase grip on the pipe ramp as well. The silicone we used was Smooth Seal 935, which provided the greatest firmness out of all 3 silicones available. And we like that because it prevented our wheels, or prevented the treads from our wheels getting torn off like what happened in the EcoFlex.
So in order to lift our arm, we calculated that we needed a gear ratio of 10. Without using a compound gear train, the only way that we could do this is to cut a really big acrylic gear with 190 teeth and a small gear with 19 teeth. Using our SolidWorks center of gravity calculations, we decided that we wanted to secure the arm in the middle of the robot so that the claw with the ball in the front would balance out the motors in the back. We had some problems with our 190 and 19 tooth gear separating, so we created an acrylic piece which secured to this shaft and the 19 tooth gear, which defined the distance between them and made sure they didn't separate.
We made the claw design such that the bottom plate rests right above the ground, so that the lower protrusion of the claw rests 0.4 inches above the ground. We designed the servo motor such that it drives one gear counterclockwise, which drives the gear next to it clockwise. This opens and closes the claws.
We turned all the shafts for the gears and the wheels in the lathe. We laser cut the gears for the arm, the chassis, and the supports. We 3D printed the claw mount, and we milled and drilled the supports for the shafts.
The strategy of the competition, we're initially planning on picking up a red ball, going up the pipe ramp to maximize points, and then placing it on the top row of the tic-tac-toe grid. And over the course of the 3 minutes, we're hoping to get a full top row, and if the other team can't score points, then we're planning on just blocking them so that we don't burn out our motors.
So our desire to have well-supported shafts for both the gears and the wheels led us to design strong, singular supports on either side with multiple reinforcement points. Ironically though, this really hamstrung us later because we had a lot of difficulty taking our components apart and putting them back together quickly and efficiently. The actual assembly and disassembly of a machine is just as an important factor to consider in the beginning stages of one's design.
Scoop! Scoop!